Imagine you are falling, not through air but through time itself. 6 million years dissolve around you like salt in water, and suddenly you're standing at the edge of a cliff that shouldn't exist. Below you stretches a chasm so vast, so impossibly deep, that your mind refuses to comprehend it. Where the azure waters of the Mediterranean Sea should shimmer under the Miocene sun, there is only nothing. A void. A continental wound carved 3 kilometers into the Earth's crust. The heat hits you like a physical blow. 80 degrees Celsius. The air itself feels weaponized, thick with toxic gases rising from salt plains that extend to every horizon. You can barely see through the sulfurous haze, but what you glimpse makes your stomach lurch. The skeletal remains of coral reefs, now bleached monuments to a vanished ocean. The empty shells of creatures that once thrived in waters that no longer exist. And far, far below, at the bottom of this hellscape, hypersaline pools glowing an unnatural crimson, too poisonous for anything but extremophile bacteria to survive. This is not science fiction. This is Earth approximately 5.6 million years ago. Welcome to the Messinian Salinity Crisis, the most catastrophic environmental disaster in the last 65 million years. A cataclysm so complete that it annihilated 90% of all endemic species in the Mediterranean basin. An apocalypse that would paradoxically become the greatest evolutionary laboratory our planet has ever known. But here's what will truly shatter your understanding of natural history. This was only the beginning, because what came after the Zanclean Megaflood would make this destruction look almost gentle by comparison. The largest flood in Earth's recorded geological history. A deluge, so violent, so incomprehensibly massive, that it would fill this dead basin in less than 2 years, with water cascading at speeds of 144 kilometers per hour and sea levels rising more than 10 meters per day. And when the waters finally settled, they would reveal something extraordinary: creatures that had never existed before. Dwarf elephants, the size of large dogs, giant swans taller than the elephants they lived alongside, mouse goats with rodent teeth and reptile-like metabolisms, a world where the rules of evolution had been rewritten from scratch. Stay until the end of this video, because the strangest part isn't the catastrophe itself, it's what survived it. And what that survival tells us about a pattern that repeats across every mass extinction in Earth's history. The apex predators, the giants, the seemingly invincible masters of their domains, they all share one fatal weakness. And by the time you understand what it is, you'll never look at the natural world the same way again. To understand what happened to the Mediterranean, you first need to understand what it was before the apocalypse, and the forces that would ultimately destroy it. Picture the Mediterranean basin approximately 7 million years ago. It's not the sea you know today. It's a thriving tropical paradise, teeming with reef-building corals, ancient sharks, pinnipeds hauling themselves onto sun-warmed beaches, and a rainbow of fish species found nowhere else on Earth. The waters are warmer than today, clearer, more diverse. This is the Tethys remnant, the last whisper of an ancient ocean that once stretched from Spain to Indonesia, now squeezed between the slowly colliding continents of Africa and Europe. The Mediterranean of this era represents one of the richest biodiversity hotspots on the planet. Scientists have documented 779 species that existed exclusively in these waters. Endemic organisms that had evolved over millions of years to fill every available ecological niche. Dugongs graze on seagrass meadows. Tropical corals construct elaborate reefs that rival anything in modern Indonesia. The Eastern Mediterranean in particular harbors the highest concentration of unique species, a treasure trove of genetic diversity accumulated over geological time. But 2 forces are converging that will doom this paradise. The first is tectonic. The African plate has been grinding northward into Eurasia for tens of millions of years, slowly closing the seaways that connect the Mediterranean to the wider ocean. By the late Miocene, only one gateway remains, a narrow strait in what is now southern Spain, the precursor to the Strait of Gibraltar. This passage is the Mediterranean's lifeline, its only connection to the Atlantic Ocean, the only way fresh seawater can replace what evaporation constantly steals. The second force is climate. The late Miocene world is drying out. Ice sheets are expanding at the poles, pulling moisture from the atmosphere. The region around the Mediterranean is becoming increasingly arid, and evaporation rates are climbing. The sea loses more water to the atmosphere than rivers can replace. For millions of years, Atlantic inflow compensates. Water pours through the gateway, maintaining equilibrium. But around 5.97 million years ago, the inevitable happens. Tectonic uplift finally pinches the gateway shut. Some scientists believe it closed completely, others argue a trickle remained. Either way, the effect is catastrophic. Within 1,000 years, a geological eye blink, the Mediterranean begins to die. With no significant Atlantic input, evaporation dominates. The sea level drops. 1 meter per decade at first, then faster. The continental shelves emerge as the waters recede, exposing landscapes that haven't seen sunlight since the dinosaurs. Rivers like the Nile, the Rhone, and the Ebro suddenly find themselves pouring into an ever-deepening abyss, carving canyons thousands of meters deep as they chase the retreating water. The Nile's buried canyon extends 2,400 meters below modern Cairo, deeper than the Grand Canyon. The Rhone cuts similar trenches into southern France. These rivers are chasing a sea that's fleeing from them, and in their pursuit, they reshape the very bones of the continents. As the water vanishes, salt precipitates. The Mediterranean Sea contains roughly 5% of all the salt dissolved in Earth's oceans. When that water evaporates, the salt stays behind. Layer after layer accumulates on the exposed seafloor, gypsum, halite, and hydrite, until the deposits reach thicknesses of 3 kilometers in some locations. 1 million cubic kilometers of evaporite minerals. Enough salt to bury modern France under a layer hundreds of meters thick. The scale defies comprehension. Scientists drilling into the Mediterranean seafloor in 1970 expected to find ordinary marine sediments. Instead, they pulled up cores of rock, salt, gypsum crystals, and fossilized mud cracks, evidence of repeated cycles of flooding and drying of a basin that didn't die once, but was killed again and again over 600,000 years. At the crisis's peak, the Mediterranean has shrunk to a few hypersaline lakes at its deepest points. Dead zones comparable to the modern Dead Sea, but vastly larger. The basin floor, now exposed to the atmosphere, becomes a furnace. Adiabatic heating, the compression of air as it sinks into the depression, raises temperatures to 80 degrees Celsius in the deepest areas. The air is unbreathable, saturated with toxic gases released from the decaying organic matter and chemical reactions in the salt flats. Only extremophile bacteria survive. Everything else, the corals, the fish, the marine mammals, the entire intricate web of life that took millions of years to evolve, is erased. The Mediterranean has become a continental graveyard. But death, as evolution repeatedly demonstrates, is merely a transformation. The dried Mediterranean created something unprecedented, a land bridge between continents. For the first time in millions of years, animals could walk from Europe to Africa. And they did in both directions in multiple waves, reshaping the fauna of 2 landmasses in ways that still echo today. African gerbils crossed northward into Spain, around 5.9 million years ago, their tiny paws leaving no fossil trace of the journey across salt plains that would have seemed endless. Hippos, yes, hippos, made the crossing around 6.3 million years ago, possibly swimming through temporary waterways or trudging across seasonal wetlands that briefly formed in the basin. Early camels, ancestors of creatures that would eventually reach Central Asia, migrated from Africa to Europe, their descendants surviving in forms we'd recognize today. The traffic moved both ways. European rabbits and mice headed south, colonizing North African landscapes where they'd never existed before. The genetic signatures of these migrations persist in modern populations, invisible threads connecting animals on opposite shores of what is now a sea. But the most consequential migrations were to the islands. When the Mediterranean was full, places like Sicily, Malta, Crete, Cyprus, and the Balearic Islands were unreachable, isolated by kilometers of open water. When it emptied, they became mountaintops rising from a salt desert. Animals that descended into the basin and climbed these peaks found themselves in isolated worlds, cut off from mainland ecosystems and the selective pressures that governed life there. What happened next would produce some of the strangest creatures in the history of vertebrate evolution. Consider the elephant that would become Paleoloxodon falconeri, the Sicilian dwarf elephant. Its ancestors were Paleoloxodon antiquus, the straight-tusked elephants of mainland Europe, animals that stood 4 meters tall at the shoulder and weighed as much as 15 tons. These were giants, the largest land animals in Pleistocene Eurasia. When populations became stranded on Sicily after the Mediterranean refilled, they entered an evolutionary pressure cooker. Resources were limited. There were no large predators to fear, no competitors for food, no need to maintain the massive bodies that had evolved for mainland survival. Generation after generation, the elephants shrank. The end point was almost comical in its extremity: adults, standing just 96 centimeters tall, shorter than a Great Dane, and weighing approximately 250 kilograms. Their newborns were smaller than house cats. Scientists reconstructing their skeletons initially thought they were examining juvenile remains. The idea that an elephant could be the size of a large pig seemed too absurd to consider. But Paleoloxodon falconeri wasn't simply a miniaturized version of its ancestor. Evolution doesn't work that way. The dwarfing process rewired everything. Their skulls developed neotenic traits, features normally seen only in juveniles, including a flattened forehead and proportionally enormous brain cavity. Relative to body size, these dwarf elephants had brains comparable to humans. Their necks elongated, their limbs reshaped with hind legs lengthening and forelimbs shortening, giving them a concave back unlike any other elephant. Their feet became more digitigrade, their gait adapted for clambering over rocky terrain rather than the stately walking of their giant ancestors. Most remarkable was their life history. Histological analysis of their bones, the microscopic study of tissue structure, revealed something unprecedented for mammals. These elephants grew like reptiles. Slow, flexible, with periodic growth arrests tied to resource availability. They reached sexual maturity around age 15, comparable to their full-sized relatives despite being a fraction of the mass. And they lived at least 68 years, possibly longer. In other words, Paleoloxodon falconeri achieved extreme dwarfism, not by growing faster and dying younger, the expected mammalian response, but by slowing everything down, extending their lifespan, and developing metabolisms more similar to cold-blooded creatures than to the endothermic mammals they evolved from. They were essentially elephant-shaped reptiles, physiologically speaking. They weren't alone. Sharing their Sicilian ecosystem was Cygnus falconeri, the giant swan. If the dwarf elephant represented the minimum viable elephant, this bird represented something close to the maximum viable swan. Standing approximately 2.1 meters tall with a wingspan reaching 3 meters, Cygnus falconeri was taller than the elephants it lived alongside. It weighed an estimated 16 kilograms, at least a third larger than the biggest modern swans. But size wasn't its strangest feature. This swan had evolved for life on land. Its toes had shortened, its webbing reduced. Where modern swans are aquatic specialists spending most of their time in water, Cygnus falconeri was a terrestrial grazer. Its broad spatulate bill was adapted for cropping grass and low vegetation directly from the ground. It walked rather than swam, occupying an ecological niche normally filled by large mammalian herbivores, which in this bizarre island ecosystem were elephants the size of sheep. The giant swan coexisted with giant dormice, cat-sized rodents with skulls restructured for powerful chewing. Their jaw muscles anchored to thick cheekbones evolved over generations of processing tough, insular vegetation. Giant owls hunted in the darkness, their size expanded to fill predatory niches vacant of mammalian carnivores. Giant tortoises lumbered through the undergrowth. The ecosystem was an inversion of normal rules. Birds and reptiles grew large while mammals shrank. On Crete, the pattern repeated with variations. Lutrogale cretensis, a close relative of modern smooth-coated otters, evolved into something resembling a land otter still capable of swimming, but primarily adapted for walking and running, hunting terrestrial prey in an ecosystem devoid of large mammalian predators. On Sardinia and Corsica, multiple otter species radiated into different niches, some becoming semi-marine, others fully terrestrial, each filling ecological roles that would normally be occupied by other mammals. But perhaps the strangest island creature of all evolved on the Balearic Islands Mallorca and Minorca. Myotragus balaricus doesn't translate well. Mouse-goat is the literal meaning derived from Greek, and it captures something of the animal's bizarre appearance, a bovid with rodent-like teeth. This creature arrived on the Balearics during or shortly after the Messinian Crisis, and it proceeded to evolve in isolation for more than 5 million years longer than the entire existence of the genus Homo. The result was an animal that broke virtually every rule of mammalian biology. Myotragus was small, about 50 centimeters at the shoulder, weighing perhaps 25 kilograms. But its proportions were all wrong for a bovid. Short, stubby legs with limited mobility, a wide barrel-shaped torso, forward-facing eyes unlike the side-mounted eyes of most herbivores, suggesting poor peripheral vision, and those teeth, specifically a single pair of ever-growing incisors in the lower jaw, continually erupting like rodent teeth designed to clip tough vegetation in an environment where food was perpetually scarce. Histological analysis revealed something astonishing. Myotragus grew like a crocodile. Its bone tissue showed patterns of arrested growth periods where the animal simply stopped developing until resources improved. It reached sexual maturity late, lived far longer than any comparable mainland bovid, and possessed a metabolism that appeared capable of fluctuating, possibly even a form of torpor during resource-scarce periods. Scientists compared its physiology to hibernating bears, another mammal that evolved reduced predation pressure and can survive extended periods of inactivity. But Myotragus took this adaptation further, essentially becoming a mammal that functioned like a reptile, sacrificing speed and alertness for the ability to survive in an environment where resources could vanish for months at a time. It worked. Myotragus survived for over 5 million years through ice ages and interglacials through climate oscillations that drove countless mainland species to extinction. It was perfectly adapted to its isolated world. Then humans arrived approximately 5,000 years ago. Myotragus was extinct within centuries. Its slow movements, poor eyesight, and complete lack of predator avoidance behaviors made it catastrophically vulnerable. The same adaptations that allowed survival for 5 million years became fatal weaknesses the moment a new apex predator appeared. And then came the flood. Around 5.33 million years ago, something gave way near the modern Strait of Gibraltar. The precise trigger remains debated tectonic subsidence, lowering a barrier erosion, breaching a natural dam sea level rise, providing the final push. But the effect was instantaneous and absolute. Atlantic Ocean water found a path into the empty Mediterranean basin. What followed was the Zanclean Megaflood, the largest flood event ever documented in Earth's geological history. Recent research published in Communications, Earth and Environment has finally provided physical evidence for what had long been theoretical. Over 300 streamlined ridges in southeastern Sicily, carved by water moving at speeds up to 144 kilometers per hour. A W-shaped channel 20 kilometers wide and 270 meters deep scoured into solid rock. chaotic deposits of boulders and sediment transported hundreds of kilometers by forces no modern flood can match. The numbers beggar belief. Discharge rates between 68 and 100 million cubic meters per second, roughly 450 times the flow of the Amazon River. Peak flow possibly exceeding 100 million cubic meters per second, with water velocities over 40 meters per second. The Niagara Falls, by comparison, moves about 2,400 cubic meters per second. Scientists estimate the flood created a waterfall at Gibraltar that dwarfed anything on Earth today, perhaps 30 times taller than Niagara, with water plunging into the basin, with enough force to trigger earthquakes across the region. The weight of incoming water pressed down on the crust, causing it to slide across the underlying mantle, generating seismic events that would have been felt across the entire Mediterranean. For the Mayotragus on Mallorca, the experience must have been apocalyptic. Earthquakes rippling through the ground, tropical storm force winds generated by the rapid pressure changes as the basin filled, the roar of water audible from hundreds of kilometers away. Within months, possibly as little as 2 years, the entire Mediterranean basin refilled. Sea levels rose more than 10 meters per day at the peak. Every creature on the abyssal plains was obliterated. Every salt-adapted organism that had colonized the basin floor died. Every ecosystem that had developed during the 600,000 years of crisis was erased in what might have been the most rapid environmental transformation in vertebrate history. But the islands, the Sicilies and Maltas and Cretes, survived. The animals that had climbed those mountains remained above the rising waters, isolated once again, their evolutionary experiments preserved while the world around them drowned. And from the Atlantic, new colonizers arrived. The Mediterranean's post-flood fauna was almost entirely different from what existed before the crisis. A comprehensive 2024 study published in Science analyzed 22,932 fossil occurrences of 4,897 marine species, spanning 12 to 3.6 million years ago. The findings were stark. Only 86 of the 779 endemic species documented before the crisis survived to appear afterward. The turnover was nearly total 67% of Mediterranean species after the flood were different from those before it. The great white shark Carcharodon carcharias first appears in Mediterranean fossil records after the Zanclean flood. Oceanic dolphins colonize the refilled basin. The species we associate with the Mediterranean today, the marine life tourists swim among, are almost all descendants of Atlantic colonizers, not survivors of the original ecosystem. Even the pattern of biodiversity reversed. Before the crisis, the eastern Mediterranean, the Ionian and Levantine seas harbored the greatest species richness. After the flood, diversity decreased from west to east, the gradient we still observe today. Atlantic species entering through Gibraltar spread eastward, their numbers thinning with distance from the source, establishing a biogeographic pattern that has persisted for more than 5 million years. The recovery took 1.7 million years. Nearly 2 million years for species numbers to return to pre-crisis levels, the first detailed quantification of how long it takes an ecosystem to heal from near total extinction. What can we learn from this catastrophe? The Messinian Salinity Crisis and Zanclean Megaflood represent one of the most dramatic environmental cycles ever documented, a complete death and rebirth of an entire sea. But the patterns they reveal are disturbingly universal. First, the vulnerability of peripheral seas. The Mediterranean's isolation made it a biodiversity hotspot, but that same isolation made it catastrophically susceptible to disconnection from the global ocean. Modern peripheral seas, the Black Sea, the Baltic, the Red Sea, face similar vulnerabilities. Climate change is already altering salinity patterns, temperature gradients, and circulation in these bodies of water. Second, the timescales of recovery. 1.7 million years is not a comfort. When we discuss resilience in modern conservation, we typically mean decades or centuries. The fossil record suggests that true recovery from mass extinction events, return to pre-crisis diversity levels, operates on timescales that dwarf human civilization. Third, the paradox of specialization. The Myotragus survived for 5 million years through extreme adaptation to its isolated environment. Those same adaptations made it extinct within centuries when conditions changed. The dwarf elephants, the giant swans, the specialized otters, each was exquisitely fitted to a world that no longer exists. And this brings us to the final lesson, the pattern that echoes across every mass extinction in the fossil record. The apex predators die first, or rather, the specialists die. The creatures perfectly adapted to stable conditions, the giants that require vast resources, the endemic species that exist nowhere else. When environments shift rapidly, whether through tectonic cataclysm, asteroid impact, or climate change, generalists survive while specialists perish. The Mediterranean's post-crisis fauna wasn't populated by the most impressive creatures of the pre-crisis world. It was colonized by Atlantic generalists, opportunistic species capable of exploiting a wide range of conditions. The great white shark isn't the apex predator of the modern Mediterranean because it's the most powerful marine animal. It's there because its ancestors were adaptable enough to colonize a newly emptied basin, while more specialized competitors had already gone extinct. Evolution, in the end, does not reward perfection. It rewards flexibility, the ability to survive when the rules change. 6 million years ago, the Mediterranean died and was reborn. Its original inhabitants, species that had evolved over millions of years to fill every available niche, were almost entirely erased. What replaced them was not superior. It was merely different, adapted to a world that no longer existed, flexible enough to survive one that did. On isolated islands, strange creatures continued their experiments. Dwarf elephants and giant swans and mouse goats with reptile metabolisms until new disruptions arrived. Humans, climate shifts, sea level changes that reconnected islands to mainlands, allowing continental predators to cross barriers that had protected endemic species for hundreds of thousands of years. One by one, the island experiments ended. The dwarf elephants disappeared around 200,000 years ago when Sicily reconnected to Italy. The giant swans vanished at the same time. Myotragus survived longest, protected by the deep waters separating the Balearics from the mainland until human boats crossed that final barrier. Today, the Mediterranean looks normal. Blue waters lap against ancient shores. Tourists swim above the salt giant, the kilometer-thick layer of evaporite minerals that records a catastrophe no human witnessed. The descendants of Atlantic colonizers continue their lives oblivious to the apocalypse that made their existence possible. But the lesson remains written in fossil bones and salt crystals, and the strange, twisted skeletons of creatures that evolution created in desperation and time erased without mercy. Nothing is permanent. No adaptation is forever. No species, no matter how successful, how dominant, how perfectly fitted to its world, is immune to change. The Mediterranean will close again. The African plate continues its northward drift, and in 50 million years or so, the Strait of Gibraltar will likely close once more. Another crisis may begin. Another extinction may unfold. And somewhere, in some isolated corner of the dying sea, evolution will begin again, building new forms from the ruins of the old, creating creatures that will seem impossible to whatever observers eventually discover their bones. That is the true story of the Messinian Salinity Crisis. Not just death, but transformation. Not just extinction, but the eternal creativity of life, finding ways to continue. If this journey through deep time has changed how you see the natural world, if you understand now that every ecosystem is temporary, every species a work in progress, every moment of stability, just the pause before the next catastrophe, then you've glimpsed something profound about our planet. The Mediterranean will remind us if we listen. Its salt layers whisper of apocalypse. Its island fossils speak of adaptation beyond anything we thought possible. And its modern waters teeming with life that shouldn't exist prove that even total destruction can be a beginning. Subscribe to join us on the next expedition into Earth's strangest chapters. Because the past is not dead, it's still teaching us if we know how to read its bones. And the next story might be even stranger than this one.